Hey everybody, welcome to the OpenUSD Insiders live stream, and this is actually a robotics office hours. Super exciting. We have our host here, Rishab. How you doing, Rishab?
Yeah, Admar, hey everyone. I'm doing good. I'm excited for today's session.
I
It's
am
going to be
too.
fun with
And
getting
who
more
did you
insights
bring?
about.
Who did you bring with
Oh,
you here?
we joined with Shaurya. Go ahead, Shaurya. You can introduce yourself.
Yeah, so hi everyone. I'm Shar Devan, and I'll be walking you through some exciting stuff that we've been working here on at NVIDIA, and just excited to be here.
Yep.
Amazing, amazing. We're gonna
Thank
get
you so much
started.
for joining, Shaurya. Sorry,
Yeah.
Admar, go ahead.
No, that's okay. No, absolutely. Thank you so much for joining. It's so amazing when we're able to bring in developers from the team to come on and show and tell. So very grateful for you taking the time. We'll also go over a couple of quick things, but today this office hours is obviously focused on robotics and specifically augmented imitation learning in Isaac Lab. So we're going to go over a couple of quick announcements, but I'll go as quick as I can. I want to give a couple of nice plugs for some exciting things that are happening. But we're going to get back to the office hours in literally just hopefully 3 or 4 minutes. So bear with me as we go through these quick announcements because we're super excited to kind of promote your work out there at an upcoming event. Specifically, as it's shown on the screen, you can use that QR code to go into our showcase channel on the Discord. But we are looking to spotlight developers and robotics projects at a really exciting upcoming event. We want to hear about people who are leveraging the physical AI data set. So if this is you, go ahead and go to that QR link for our Discord Show Your Project channel, or you can message me directly. Feel free to contact me, edmar@nvidia.com. I'll be able to provide the link to the full Hugging Face collection and some background on the Groot data. We'll put those links in the chat as well. But ideally, we want any videos or images of projects that you've used the data set for, and with your permission to share it, along with any input on how the data has helped you or unblocked your work. So super exciting. We'd love to highlight your work. Get in touch with us if that's you. We had an amazing launch. Oh my gosh, store was just insanity last week. So super excited, and this is a quick follow up on a great hackathon that's happening in the Bay Area, October 25th and 26th. This QR code will actually bring you right to the registration page if you're interested on leveraging Jetson Thor at the Embodied AI Hackathon. I hope if you're in the area, you could participate. It's going to be a great networking event. Also, look at those great people helping participate, including Seed Studio, Hugging Face, and Hackster. So follow that QR code. If you need information, we'll also put it in the chat. Feel free to follow up anytime on our Discord server if you need more. We're happy to help you. This is also super cool. Jetson Thor unlocked real-time reasoning for general robotics and physical AI. This is actually an article. So go to this QR code and you'll see the full article on this. This is going to be a really exciting time with information coming out from not only from NVIDIA and our partners, but also from developers, from companies in the community. Follow on that blog for more information about all the exciting projects that are coming up. And of course, we have our community resources here, future upcoming office hours, of which we have OpenUSD office hours and also Isaac Sim and Isaac Lab study groups, where an OpenUSD study group where you can talk to developers in the community, exchange ideas, talk about how to solve problems. Really good opportunity. Also, our live streams and other events are located in the events forums for official support. Although for Isaac Lab, it's a little different, right? Isaac Lab, Rishab, people should go to the GitHub for support.
Yep, Admar, that's correct. For Isaac Lab, opening up a discussion on GitHub is probably the best way to get started if you're running into problems or if you're just looking for support in general.
Okay, that's great. So Isaac Sim, you want to go to the forums, which is that link. Isaac Lab, go to the GitHub. We could put that link in the chat. That Discord QR code will bring right to the Omniverse Discord server, which is a fantastic place to get support from the community. Other developers who are very actively engaged, some with lots of experience. I see questions answered there very quickly, so feel free to leverage that Discord server. And then our community page, which lists our ambassadors, is there also. All right, so this is a super exciting also announcement I want to make. This has to do with an exciting hackathon, which was just announced just a couple hours ago, actually. I'll share my screen here so you guys can take a look at the page. We'll also post this page on in the chat. But this is basically organized by none other than Lychee AI, or Muramar Bey, as he is known officially, in collaboration with Revel. They have just announced an NVIDIA Isaac Sim hackathon. This page here we'll post in the chat We'll give you all information. You can now register now up until midnight on Saturday. That's CEST. The link, again, will be in the chat. But look at this. The challenge, there's a nice video challenge here, YouTube, describing everything that they're looking to accept projects for. Judges will be announced over the next coming weeks. Those are the first 3, but some really nice surprises in store. And look at these sponsors. Amazing people, amazing companies. This is going to be a really fantastic event to watch. We hope to actually have this on a upcoming live stream. So we'll be highlighting this on LinkedIn throughout the course of the hackathon. We highly encourage people to get involved. I know we're going a little bit over. The last thing I want to announce is NVIDIA GTC coming up in actually October, end of October. So this is the first time we're doing a GTC conference in Washington, D.C. This is going to be super exciting. The sessions were all just posted yesterday, I believe. So all the sessions are now live for looking. You could look at the different workshops and the sessions. Here you go. There's a nice GTC discount code there for 20% off of your conference pass. Jensen himself will be actually providing the keynote at GTC on October 28th, and that'll be live streamed. So anyone who in the world can watch this live. You don't have to be at the event. But I do hope you can come, because look at some of these people you'll be able to see and hear from, including our good friend Rev here. This is going to be a really fantastic few days in Washington, D.C. I hope you can attend. We also have some great things planned for the community members that are attending. I'll be going, so look out for LinkedIn posts from me. Also, we have a WhatsApp group specifically for people who are attending, so we can help you with networking. There's also a brain date, which is part of the GTC app, which will be live and up and running for just GTC DC. Anyway, lots of exciting stuff. But let's get into the meat of today. We have a lot of people tuned in for this office hours. Again, we're going to cover augmented imitation learning in Isaac Lab. And my wonderful colleague and host here, Rishab, has brought in his great colleague here to go over some more details. So Rishab, I'll let you kick things off and give a nice overview of what people will be learning today.
Sure. Thanks, Admar. I think that was really cool. We also have hackathons upcoming, GTC DC upcoming. I think exciting time for robotics in general. So I think we can get started straight away. I know we've got some questions coming in the chat, so we'll pause in between as well while we're going through slides and a few other things to answer them to our best ability. But I think I'm going to now give it over to Shaurya. He can maybe start presenting his slides, and we'll take a deeper dive into what imitation learning is and how you can augment your data and do cool things with the Isaac Lab. So over to you, Shaurya.
Yeah, thanks, Rishabh. So hello again, everyone. And yeah, as Rishabh mentioned, I'll be walking us through the augmented imitation learning workflow that we have developed under Isaac Lab. And let's just dive right into it. So here's the outline of how we'll go about this. So first, I'll introduce the general workflow and why we need this, and what's the main purpose this workflow is meant to serve, and then I'll actually go over the workflow or the pipeline itself in a little more detail, and then I'll cover a little bit about Cosmos Transfer 1, which is one of the models that we use in this pipeline. And then we'll have a live demonstration, and then we'll go through some tips and findings that can be useful for maximizing the quality of the data generated using this pipeline. And then finally, we'll go over some results that we have come up with based on this data. So let's get into it. So what is augmented imitation learning? To put it simply, it's just a pipeline to help users generate realistic demonstrations for robotics. And it has been developed as an extension on top of the GR00T-Mimic workflow, which I believe has been covered in one of the previous sessions, where you basically take a few human teleoperated demonstrations and scale that up to a large-scale data set using this amazing method of GR00T-Mimic. And now, once you have these demonstrations generated using simulation, IsaacSim, basically, then the question comes that how do we make these demonstrations more realistic, or make them mimic the real world more closely? Because the simulations you get from Brute Mimic alone are usually very synthetic and, in a very perfect environment, without any of the real world effects that we see, such as changes in lighting, shadows, reflections, background objects, and things like that. So so to address this problem of getting more realistic demonstrations and realistic recordings, so that the robot learns to deal with these phenomena, we came up with a pipeline that basically makes use of Cosmos, specifically the Cosmos Transfer 1 model, where we take the data generated from the group mimic workflow and simply feed it to this model, um, the Cosmos model, along with some user specified prompts. The video an example where we have the left video is a video that we got from Brute Mimic in IsaacSim, and then the video on the right is the output we get from Cosmos Transfer 1 after feeding it some appropriate data, hyperparameters, and prompt. Um,
A
and
quick question here, Shaurya. So
Sure.
just for a step back and making sure, like, I'm not sure if everyone would be familiar with Groot Mimic is like to understand like it's a framework which will help you augment the data, not augment the data, but it's going to help you scale up the synthetic data which you might have been generated through the
Mhm.
real world. So you have like real world teleop data, you can like, use Groot Mimic and really scale it up to like many demonstrations. So I
Right.
think like is and that's pretty useful for imitation learning in general. So the augmented part over here, is that like referencing to the Cosmos augmentation itself? Like because like otherwise imitation learning is like you have some human uh, gather data sets or teleoperation data which you can scale up, but the augmented part is it like coming from Cosmos transfer?
Yes. So basically, the Cosmos transfer doesn't generate the demonstration on its own, of course. So for that, you already need to have some sort of samples or demonstrations, either the human teleoperated examples or the ones that you got from Brute Mimic, where you have already collected the robot data, like the way the positions of the joints, the positions of the objects, or of the cubes in this particular case, and so on, as well as a camera recording um, of the demonstration or the trajectory itself. So now, once you already have this data, but now you also want to make it more realistic looking. So for that, we use Cosmos. That's where Cosmos comes in. So it doesn't generate a trajectory or a sample on its own from scratch. Like, it's not like I just feed a prompt and it just generates this video on the right side. Instead, I feed the video plus a prompt specifying how I want it to change the input video, and then it augments that as per my instructions, uh, and makes the camera recording that you have of the demonstration look different or more realistic.
Makes sense. Thank you
Um,
so much. I think that basically highlights the point that, for example, if I've got maybe like 20 human demonstrations,
mhm.
so with Groot Mimic, I can scale it up to like maybe 1,000, 10,000, depending what sort of a use case I might be looking at. And to add in the augmentation for the use case specific, maybe in terms of lighting, background, material, stuff like that. That is where like Cosmos Transfer really comes into the picture and can help augment your data set even further. So I think that sort of encompasses the whole end-to-end workflow which you described.
Yes,
Okay,
that sounds about right. Yeah.
okay,
Yeah,
thanks.
and this is a really important contribution or really important workflow, I would say, because if you have ever worked at all with training robot policies or robotic models in general, you know that the biggest problem, or one of the biggest problems in robotics, is just the lack of data.
Yep,
So and then, even if we are able to come up with synthetic data um, for that problem, at the end of the day, there is a wide gap between the synthetic data and what is actually encountered in the real world, which makes it difficult for robots to generalize to real world scenarios. So the problem that we're trying to address here is to bridge that gap, where okay, you have some synthetic data. Um, Now we can make it look realistic and make it mimic the real world as closely as possible. So that is the real problem that we're trying to solve here, and it circumvents the painstaking process that you have to go through for collecting real world data at scale. Um, and it also helps with making sure that the data is diverse, because here, as the user, you have a lot of freedom with the prompts that you feed to the Cosmos model for augmentation. So that way you can also make sure your data is diverse, so that your robot can generalize to more and more different scenarios and situations. Whereas in the real world, that is another challenge, that even if you're collecting real world data, to have it be diverse um, is a very difficult thing. So this way we are able to solve multiple problems at the same time.
Super cool.
Um, yeah. So let's move on to the actual workflow now. So don't worry, I know this figure looks a little complicated, but we'll go through it step by step. Um, so here, the workflow is highlighted from start to end of all the steps involved in going from human teleoperated demonstrations all the way till so first, of course, you need to collect a few demonstrations, and for that also we have a workflow specified in the Isaac Lab documentation, where you can use the Apple Pro to collect some data, um, and use that data to kind of bootstrap the Groot Mimic pipeline, which will then scale up those few demonstrations. Let's say you collected just 10 demonstrations. Now you can just feed that to Groot Mimic, and it'll generate 1,000, 10,000, or 100,000 demonstrations on top of that. It's up to the user how many demonstrations they want. Um, but now, once you have this Groot Mimic generated demonstrations, which have been, you know, uh, collected in simulation, now you feed these demonstrations to Cosmos. But the process is not straightforward. That okay, now I have this data and I just give a data file to Cosmos, and it just takes that data as is and does what it needs to do. Instead, there are a few steps in the middle that I'll go through in a little while. Uh, but the crux is that one of the things you need to keep in mind while scaling up with Groot Mimic is you need to make sure that the data as it's being generated has the camera setting on, so that it does actually record videos that can then be fed to Cosmos, because we also have certain environments and certain tasks for which you can switch off the camera, which means no camera data will be recorded for the new trajectories or new demonstrations that are being generated. In which case, you can't really use Cosmos to augment that, because there is nothing to augment visually. So you need to make sure that the camera setting is on to make sure that the uh, simulation records the camera data as it generates new trajectories. And then once you have this recorded data, then you can actually feed it to Cosmos along with a prompt. Here I've given an example prompt. And then, yeah, you can finally get this output video of a realistic looking uh, real world setting, where you have a robot arm picking up cubes and stacking them in a office setting. So let's go into detail of what each step is in this particular workflow. So first, as I mentioned, you have the mimic data generation step, where you bootstrap the mimic pipeline with a few uh, human teleoperated demonstrations to scale up the dataset significantly to the extent needed. Then you need to actually extract these recorded videos that you have into MP4 format. So the data that comes out of Group Mimic is by default generated and stored in an HDF5 data file format, where it contains the robot positions, joint positions, object positions, and various other details in addition to the recordings itself in that one data file. So we provide a script under Isaac Lab to actually just record or just extract the camera recordings from the HDF5 file and save those as MP4 files. And one thing to note here is that we are not only dealing with RGB videos, we are also dealing with our depth and segmentation modalities. And these, again, are um, easy to record with Isaac Lab and Isaac Sim. Like we have already provided an environment and uh, various settings you can tune to make sure that these two additional modalities are also being recorded, and not just the RGB camera data. So the script we provide to convert it to an MP4 format makes sure to parse all of these modalities as needed. Then we actually come to the Cosmos Transfer 1 augmentation step, where we feed all of these videos. And what I mean by all of these videos is we feed all three modalities, the RGB, the depth, as well as the segmentation, to Cosmos Transfer 1, which has the capacity to take in multiple modalities as inputs to control the generation process. And then we also feed the model a prompt, and it uses the prompt as well as the input videos to come out with a output augmented video as per the user prompts. And then finally, you this is a very crucial step that is very easy to overlook sometimes, that now once you have these videos, you need to actually package this uh, with the corresponding demonstration data. So what I mean by that is, the robot, like for each trajectory, you have this information like the robot positions, joint positions, etc. So now that remains the same even if the video has been augmented. That all of that data remains the same because the trajectory that is being followed in the video, as you can see here on the right, is exactly the same as the inputs that were fed to the Cosmos model. The only thing that has changed are the visuals, like it has added textures to various parts, changed the lighting, shadow, reflections, um, but it has not changed the trajectory itself. So that trajectory information that you had originally obtained from Groot Mimic along with the recordings remains relevant and still pairs with the same sample that you have here. So in this step, what we are trying to do is take this augmented video and put it back into HDF5 format, but with the corresponding um, trajectories information for other things like the robot states. So this is a very important step, and this is done based on the demonstration ID. So every trajectory or every demonstration has an associated ID. So we make sure to pair or match the correct augmented video with the correct information or the correct data, robot data.
And I think this
So
also highlights like the aspect that the Cosmos models in general, like predict transfer, like transfer in this particular use case, can still understand the underlying physics of a particular video, and it is able to augment the data, making sure like those laws are obeyed. So, like you mentioned, like the trajectory itself for the robot, which is probably physics based in simulation and is also going to be the case in the real world, that
yeah,
remains the same. Like Cosmos does not alter that, but any other things from the environment, from like the visual perspective, materials, textures, lighting, like all of those can be like directly modified through a prompt, and that really
mhm,
helps like scale up your synthetic data in general. So it's pretty useful in that way.
agreed, exactly. And that is, like honestly, when I first started working with this model, it felt like magic. Once it was actually working at this scale, because um, here you're just feeding the model some visual data, that too just from a single view, and you're not even feeding it the robot data that you do have at hand, but you're not feeding that to this particular model. And just based on that recording or just based on that visual, it is able to understand, okay, so this is how the robot is moving, this is how the cubes are placed, and this is how the cubes are moving over time and interacting with the robot arm. And it in the prompt, if you just mention that you want these things to remain the same, and then of course you also tune a few hyperparameters of the model itself, but just with a few of these minor changes, and you're able to make sure that the model understands that, okay, I need to retain this core information, but I have the freedom to change other things visually. The only thing that I'm absolutely not allowed to change is the trajectory or the movements itself and the positions of the objects, or of the core objects itself. So
Right, because
it's
like those
honestly,
have been obtained in that generation process itself as like the demonstration. So if we do actually end up some way changing those parameters itself, like the ground truth and like the RGB representation, like they won't correspond at all. So we would need to make sure that all the join states and all the other observations which are needed for our framework remain the same, and
yeah,
only augment data from the standpoint which is useful apart from like the robot state itself.
yes, exactly. So it's honestly a very useful model that is able to achieve this. It's amazing, at least to me. So yeah. Um, but anyways, let's move on. I guess if there are no more questions as of now.
We can take a few questions actually. We've got a few questions
Okay,
from the chat. Let me actually
sure.
bring them in here. We can take a quick pause. I think I earlier saw a question for wanted to learn Isaac Sim for RL. I'm not sure like that's probably entirely correct. It's like got Isaac Sim for simulation and Isaac Lab for RL and imitation learning. But yeah, certainly there is overlap. So here I would suggest the best place to go is the robotics fundamental path, which we've got on DLI, and that's completely hosted. So
Um,
getting started
sorry.
with Isaac. So getting started with Isaac Sim courses and Isaac Lab courses, we can paste a link over here. Let me see if we can get it. But yeah, well, I can actually quickly share my screen. That might make it easier to. Sorry, sorry. Just a sec.
No worries, no worries.
Yeah. Uh, so this is what we have on the robotics fundamentals page for DLI itself. So getting started with Isaac Sim, we've got 5 courses for bringing your assets in SDG, software in the loop with ROS, and even hardware in the loop. So super useful. And from the Isaac Lab standpoint, how do you get started with training your own robots in Isaac Lab? What are the types of workflows and how you can like get started with it? So something which might be of interest and relevant to this session as well is like Groot Mimic, which we just touched upon. We've got a course which is coming soon over there too. So just we'll let you know obviously on the office as well, but it's coming. So this is the best place to get started. And hopefully that answered that question. And let me look at a few other ones. You've got where is Isaac Lab located? So you can go to the GitHub directly and you should be able to build Isaac Lab from there. Got documentation as well, which is going to be helpful. Looking for next questions. Sorry. Okay, we've got a question for does RGB improve performance? Shaurya, any insights over here? I know like Cosmos transfer takes in a lot of modalities, like that's why we had like
Mhm.
depth and segmentation. I'm not sure if you do need a modality to get started, like you can't use Cosmos transfer without any sort of video. So I would say it's like a bare minimum to get started, but
Yeah.
is RGB the best way to go or any other modalities as per your experience?
Um, okay, so yeah, as you mentioned, you did need at least one modality to feed to Cosmos Transfer 1, because yeah, it's not a text to video generating model, it's a video to video generated model. So it needs at least one modality as input for sure. Now, by default, it expects an RGB as input. So the model works best with RGB data, generally speaking. But in this particular use case, to use it with the group mimic and the data that we get from there. Um, one constraint that we had was that the recordings that we get from group mimic, or sim in general, we had to keep them at a slightly lower resolution compared to normal videos, um, and the reason for that was so that we could actually generate data a little more quickly, and not have to wait around, because as you increase the resolution of the recordings, that kind of increases the compute and the load on the system.
Yep.
So we had to find a sweet spot, so we went with a slightly lower resolution recording. um, so now when we were working with this lower resolution setting, I mean, Cosmos still works, of course, and as you saw in the examples that even when you would see like a sort of grainy, pixelated input, the output would be like high resolution, very you would be able to see finer details, and you wouldn't see any pixelation effects from Cosmos. But um, we found that if we fed this just this low resolution RGB video and no other modalities, then the model would not do very well, because as we saw even in the example input videos that we're feeding, that the RGB video, some things are very ambiguous, that makes it difficult for the model to understand a few things about how the robot arm is moving and how it's interacting with the cubes, just because of the low resolution. So that is why we found that feeding it additional modalities helped a lot. In fact, I would say for this particular use case, it would be better to feed um, just the segmentation, um, instead of just the RGB, and that is what we found gave slightly better results. Still not great, but the segmentation uh, worked as a better modality in this case, because um, from the RGB video, it was difficult for the model to actually differentiate between different parts of the scene, because of the poor quality, whereas the segmentation directly gives that information, and it was still able to do a decent job with just that. Uh,
Makes sense. Thanks so much, Shorty. I think that also sort of like highlights an important point for Cosmos transfer in general is like it has a support for multimodal inputs. So RGB, shaded segmentation, depth, edges, like something which we even covered in the previous office hours. So all of these can be used as the input itself for Cosmos transfer, and there is some hyperparameter tuning you can there to do to is in terms
mhm,
of how much weight you want to assign for each of those inputs. And like in this case, Shaurya mentioned that making sure that the objects and the robot themselves like retain their state in essence while the rest of the data is being modified according to your prompt. So that is where like it's really important to make sure that segmentation and maybe example depth as well, additional information which goes into the model for doing something like that, this is super useful. So that makes sense. We can take maybe a couple of more questions before we move on to the next slides. I know we've still got a lot to cover.
sure.
We've got, is there an existing example repository for this example? So we do have, this is a tutorial which is already available, and yep, so there is an augmented imitation learning tutorial on the Isaac Lab documentation itself. So that will walk you through in more detail in terms of each of the steps which Shaurya just described, and that's something which we'll touch upon in the presentation too. But all of this is already available with Isaac Lab today. And we've got another question. Interesting. How about the speed? Because it looks like need to use multiple times to generate the data sets. I think Shaurya can provide more insights there, but just with the nature of the workflow, like we can have the augmented data being iteratively generated through prompting itself. So like I think the only thing which is like uh, important in that sense from a speed perspective is maybe the instance type on which you run the Cosmos transfer models themselves, which tend to be compute heavy, for example, H100s and stuff like that. But apart from that, the only barrier for you to be able to generate more data is going to be like prompts in general and maybe the number of samples you have. So any insights over there, Shaurya?
Yeah. So okay, so there are two parts to this. First is the mimic side, of course. And there, the time it takes to generate the data, um, honestly depends quite a bit on various factors. For example, one of the factors was the resolution of the camera recording that you said actually affects the time it takes to generate the data, as well. But for this particular workflow, when I generated 1,000 demonstrations from Root Mimic, at our end, it took us about a few hours, about 4 to 5 hours, um, because again, even though it's a low resolution recording, it's not very low res. We kind of went with the trade-off where it would take a few hours for Group Mimic to generate 1,000 samples, but not um, more than a day or not more than half a day um, to do that. But as I said, you have various hyperparameters that you can change that really affect um, how long it takes to generate that data at that level. Now, for the second part, um, where we deal with Cosmos Transfer One, here things are a little more definitive because here things don't change that much with the hyperparameters in terms of the generation time. Other than, of course, it still depends on the compute that you have, but we ran it on 8 H100s at our end, and it would take us about 3 minutes, 2 to 3 minutes to generate per video, each video. Um, and we ended up generating 1,000 videos from Cosmos, or rather, augmenting 1,000 videos um, with Cosmos. So yeah, you can just scale that up, just multiply 3 by 1,000, and about 3,000 minutes. Someone can do the math on how long that is in terms of hours, but um, that's how long it took us to run this on 8 H100s, which is the recommended compute for running Cosmos anyways.
I'm sure it makes sense. I think there are more questions, obviously, but we can get back to our slides and the presentation, and we'll take them as we move ahead. I
Sure.
can stop sharing and you can go ahead.
Yeah. Is my screen visible again?
Yep.
Okay. So yeah, let's just dive right into the main model behind this entire pipeline, which is Cosmos Transfer One. Mentioned earlier, um, where each modality that you feed is processed in some way through a kind of uh, encoder, and then the relevant information is extracted from each of these modalities and used during the generation process from transfer one. So in our case, we make use of the RGB depth and segmentation modalities. Um, and one modality that we did not touch upon earlier is the canny or the edge modality, where basically you feed it a video, the same video, but now it only contains the edges highlighted in the video, and everything else is just blacked out, which you can get fairly easily by just feeding the RGB video through a canny edge detector or even any other edge detector, um, and you just generate like a sort of outline of all the objects in the scene. So that is a fourth modality that can be fed to transfer one. While we do not generate that modality in Isaac Lab, in the group mimic workflow, um, we still feed a control weight for this in the hyperparameters for transfer one, and just by feeding a non-zero value for this control weight, um, and the model sees that we want to use this modality as well, but it sees that we have not fed any input for that particular modality. So then the model runs an edge detector in the backend, you know, um, and generates the required modality, and then actually runs the generative model to do the augmentation with all four modalities. So, and then this another thing to notice, um, it would also be possible. It's also possible to not feed any input for the depth and segmentation, um, but give a non-zero control weight, and again the model will use you know certain other existing models to uh, first infer these modalities on its own just from the RGB video, and then actually run the generative model itself. Um, but in
Well,
our
this is
case, since we have
super cool. I did not know about this too. This is new information for me that even if you don't have the actual inputs themselves, you can like provide the weights, and there's going to be some other model in the back end which is going to handle like generating depth and segmentation and canny edges. So that's pretty cool. Yep. Sorry, continue.
yes and no. Yeah, I mean, I agree. I completely agree with you. I mean, it's just that in our case, we didn't like we had access to the ground truth depth and segmentation since it's available in Sim. So we did not need to make use of this particular feature of Cosmos, but um, yeah, it's a good feature to have, and we do use it for the canny edge detector at the very least. So yeah, it's definitely very cool to see that. And then of course you also feed a prompt to the model, and now once it has all of this information, it takes the relevant paths from each, um, and uses all of that together to generate this final augmented output. So the model is really um, trying to work a lot um, with a lot of this information, and make the best use of it. So yeah, we'll dive deeper into why we chose these particular weights in a little while, but for now, these are the weights we used at our end for generating the data that you see on screen. Now, I think we can go and yeah, I can go through a live demonstration of this workflow just to see how everything works. So, just to be sure, so you see my terminal, right, Rishabh?
Nope, sorry. We can see your slides here. So
Let's see, yeah.
you can try
Okay, yeah.
sharing and
Is it
yeah.
visible now?
Nope. Okay.
Um,
Whoa. Oop, nope. Not your terminal, but yeah, it's visible now.
okay, it's visible now, right? Okay, great. So yeah, I've already set up Isaac Lab and Cosmos locally just for this time, so I won't be going through those things. So the first step is to actually generate some data with Mimic. Here, I already have some annotated data set, annotated data of human teleoperated demonstrations. Um, so I'll just be directly going to the brute mimic generation step. So here I've just set the data generation to occur with two environments, and to only generate two trajectories or two samples for the sake of time. So let's just run this and see. Also, I've switched off the accumulator. You'll see the logs as they come up. Um, and yeah, this just takes a few minutes. So yeah, let's just wait for that. So yeah, the setup seems to be complete for the environment, and now the actual data generation will kick off. Yeah. Okay. So yeah, I found yeah, it's been able to generate one trajectory successfully so far out of two attempts. Yeah, it usually takes a few attempts to generate a successful trajectory, but that is expected behavior.
While we're waiting for that, do you want to take a few more questions, or if you want to talk about what's happening in the back end? And guess like totally up to you.
So actually, it just finished running.
Okay, we're good then. Yeah, go ahead.
Yeah. So okay, so now let's see. So this should have been saved to the demo folder, and yes, here you see it saved. The successful trajectories under demo.hdf5, and it also saved the unsuccessful samples or unsuccessful demonstrations in a separate file in case you want to see what's happening there. So now let's actually go to the next step where we extract the recordings from the HDF5 file and save them as MP4s. Um, Yeah, so here we provide the script HDF5 to MP4 for that in Isaac Lab. This runs relatively faster, it just takes a few seconds. Um,
I think while we
Yeah.
wait, oh, I
I think
seem to
every
be
time,
always yeah
yeah,
getting questions in when we're almost done with the script. Sorry, go ahead. Did we lose Shaurya?
go check out the videos that we've gotten. Yeah, so this is
Okay,
the RGB video, and again, as I mentioned earlier, you should note, the low resolution and the blurriness or the pixelated nature of the video. Um, Here we have the depth for the same, and then here we have the segmentation, and yeah, and then of course we have another uh, trajectory or another demonstration as well. So now we have the MP4 data as we need it. So now let's actually go to Cosmos to augment that data.
a
So
quick
here,
question, and Shaurya, I think I just found that it's
sure.
relevant to what we had over here in the videos too. So, any reason for the arm jitter? Is it because of like maybe Groot mimic, or what do you think? Like, uh, is it some other reason for the jitter itself?
Oh, for the jitter, honestly, that's an artifact of Groot Mimic um, itself. So, the way the method works to generate new trajectories or new demonstrations is not, of course, it's not perfect. How it works, or the gist of how it works is it randomizes the positions of the cubes and the robot arm in every new demo, and then it you know infers the relative transformation between the original one of the source demonstrations, the human teleoperated demonstrations, versus the new randomized positions of the various objects, and then it infers the transformation and applies the transformation to the trajectory followed by the robot arm in the human teleoperated demonstration, and then applies that um, to actually pick up the cubes and complete the task. um, so now there are two sources of error that can lead to this jitter that we saw a little bit. So the first source is, of course, the human demonstration itself having a certain amount of jitter and not being completely smooth. And the second is that the way the group learning method interprets um, the source demonstrations, it divides it into subtasks. Um, for example, the first subtask could be the robot arm going towards the green cube. Second subtask can be actually picking up the green cube. The third can be placing it on top of the blue cube, and so on. And then it transforms each of these subtasks independently. Um, so since all of these are um, transformed, or all of these different parts of the trajectory are transformed independently, it can lead to a certain amount of jitter because the trajectory is no longer completely smooth, um, if that makes sense.
Makes sense. Thank you for clarifying that. Maybe we can proceed with the next steps.
Okay, sure. Yeah, so here we'll just be running Cosmos. I'll be feeding it the RGB, the segmentation and depth. Here I've just written a very simple script um, to take these inputs and run Cosmos transfer one. So let's just do that. Um, and yeah, right now I've changed a few hyperparameters to run it a little quickly, but um, the actual run of Cosmos to get good quality videos would take about 2 to 3 minutes usually. But yeah, here we have the videos being generated. Oh, first, before I go to the video, I can show you some of the configurations that I use for this. So most of the config I just mentioned it in this JSON file, and then that was read by the script. So here you have the prompt, a robot arm picking up and stacking cubes inside a high security military robotics testing bunker, and so on. And then you have various other hyperparameters that again I'll dive into in a little while. But here you can see that we have a control weight set for the edge modality as well as for the RGB modality, which is referred to as Viz for the model, as well as a path for where to pick up that modality from. Um, I mean, this path is overwritten actually by my command line argument, but I've just mentioned it here in the config for easy reference. And then same is uh, there for the depth and segmentation modalities as well. And then here you have a few extra hyperparameters that help control the generation process. Um, but yeah, we'll get into them in a little while. But let's go take a look at the videos that we have now. I only generated and yeah. Um, so Cosmos has done its job now. And then the final step before actually training any robot policy is to compile this data with the original um information of uh, robot states and cube states and various other things from the original trajectory that we have from Group Mimic. So for that, we um, yes, here we oh sorry, not here. Yeah, here we provide another script to just take this um, data and compile it with the original trajectory information and spit out a single HDF5 file that can then be used for training any robot policy. So here you have yeah, the input file. This is from the group mimic data that we had generated. So this is where all the robot states and the other information are stored, where we need to pick it up from. Then the videos there, this basically mentions where the Cosmos data is located, and then finally the output parts. So, yeah. Oh wait, I think I fed, yeah, I fed the wrong. Oh no, it's right. It's now. Yeah, I think we can take questions. This takes a little while. I don't want it to happen that oh, and it's finished already. Okay, it's just every time.
It's just a luck today. It's okay.
Yeah, but yeah, basically, yeah, this HDF5 file has now been generated, and we can now use this to train a robot policy. I won't be actually training a robot policy because we need a large scale data set for that. Just a single trajectory is not enough. But more details on training a robot policy and running evaluation on it are included in the Isaac Lab documentation, so you can always refer to that there. But now I think we can come back to the slides, and that covers the demonstration. But if there are any questions for the demonstration, I'm happy to take them before we move on.
Uh, I think we've got general questions about. I think we looked at the arm jitter one. God, is physical data necessary for generation of synthetic data? I don't think you need physical data for generating synthetic data. Like, you probably might want to combine both of them in some way for training a robot to do something, but without access to any real world robot or sensors, you can set things up entirely in simulation and still be able to generate data and train things there. So not entirely necessary, but depending on most use cases, probably you might need a mix of a little bit of both so you can get your results. I hope that answered the question. Seen that same one a few times in here. I think we have a question about what do the numbers in the parentheses represent. Uh,
Oh, are you
so I
referring to this slide
I think
here?
it was the control weights themselves, like for each of the
Yeah,
modalities, like the weights which we had. So it was probably that. Yeah,
yeah. I'll
these
be
ones.
going
Yep,
into
right.
them in a little more detail, but
Sure, I think then we can continue
yeah.
with that. Yeah.
Okay. So, okay. So yeah, now we actually get to various tips and tricks to keep in mind to make sure you get the best possible augmented data out of your Cosmos model. Um, so first, it's the most important thing is the prompts itself that you feed to the model. Um, so here are various tips that I have found. that helped me get better and better outputs from the model. First, you need to specify very clear instructions for what the model needs to do, and it's better if you specify um, specific instructions for each object and region and the way the model should handle it. So, for example, here in the bottom, I've included an example prompt on the right, and here you see it's fairly big, but if you take a closer look, it includes details on how to change the table, what texture to apply to the table, what kind of lighting is present in the scene, what objects and what activity is going on in the background, what texture to have for the robot arm, what color and cube texture to have for the cubes. Um, an important thing to note here is that I found it helps significantly when we specifically mention in the prompt that the cube's colors have to be retained from the inputs, and even the order in which they are stacked should be the same as the order they are stacked in the original video. Um, Without this particular instruction in the prompt, there would be some samples where the colors of the cubes would change, or the order of the uh, cubes would change. Like the trajectory would remain the same, but then let's say one of the cubes was red in the original video, now it would become blue, and then one of the others would become red. So that would change the order of the cubes being stacked, which completely changes the task as compared to what we have specified in this workflow. So it was really important to actually mention this to avoid these kinds of changes. Um, but for everything else, we mentioned exactly how it needs to change it, what texture needs to be applied and things like that. So it's very important to be clear and specific about each region and each change that you want to see, and even things that you don't want to change. Then the second thing is it we found it was always better if we gave more conventional and realistic settings. So, for example, here, oh, my bad. Here on the right, the example says, a robot arm is picking up and stacking cubes inside a luxury penthouse showroom during sunset. This is a little more realistic compared to, let's say, a robot arm is picking up and stacking cubes inside a movie theater with a movie underway in the background. Um, so, this is what I mean by realistic and more conventional settings. That settings that are more um, coherent and expected for the particular task at hand. Um, Generally, the model does better with those kinds of prompts. And then the third point is it's kind of related to the previous point that sometimes you can mention changes for different aspects, but the changes mentioned for each aspect maybe don't align logically. So again, for example, here you have a robot arm picking up cubes inside a movie theater, but then it's mounted on an ancient stone table, which doesn't, if you really think about it, doesn't make sense. Why would you have an ancient stone table in the middle of a movie theater or something like that? So we found it always helps if you have coherent um, prompts or coherent instructions for all of the aspects together. Um, it's not a hard requirement. The model still manages to be creative and deal with creative prompts, um, but it just works better in terms of realism if you give more coherent and logical prompts. And then finally, it's also important to preserve key details, okay, which I've already covered previously, like you need to mention the things you want to keep unchanged. Um, but yeah, those are some of the things we found work best when coming up with prompts to augment the video. We have provided some reference template prompts in the Isaac Lab repo that can then be used to construct random prompts. So what I mean by these reference template prompts is that we divided the prompt into various different parts. So one part is for specifying the table texture, one is for the lighting, one is for the background, and so on. And then for each of these parts, we have provided a list of about 15 to 20 templates. For example, you can have a wooden table, you can have a stone table, you can have an oak table, a steel table, and so on. So we have provided 15 to 20 such templates for each of these aspects, or each of these parts, and you can just randomly sample um, one of these templates for each of these parts and put them all together to create a random prompt. Now, granted, this will not adhere to one of the principles that I mentioned here, that keeping the prompts coherent with each other or logical um, with each other, the different parts of the prompt. But as I said, the model still manages to generate decent augmented videos even um, without that. So you can use this if if you don't want to go through the process of coming up with random prompts on your own. So yeah, now let's move on to the next set of hyperparameters. So these are the most important hyperparameters that we found affected the quality of generation for our use case. So the first is the sigma max. So this essentially um, this hyperparameter specifies the level of noise that should be added to the input videos, or to the input modalities, um, before applying the augmentation process, because basically transfer one is like any diffusion model, um, that it adds noise and then it denoises that to produce a new video. So um, here the range you can specify for this hyperparameters is from 0 to 80. And usually the higher the value uh, that is given, the greater the visual changes you'll see, the greater degree of augmentation you will see, and you'll see more creativity and realism, but you'll also see lower fidelity to the inputs. So in that case, if it's, let's say for example, if it's set to 80, it's possible that in some of the generated samples or some of these generated augmented videos, the trajectory may not be completely preserved, um, because of the high value for this hyperparameter. So it is important to find that sweet spot where it is it has the freedom to be creative and produce realistic outputs, but still adheres to the input, or at least to the core parts of the input, um, as uh, much as possible. So for that, we found that generally giving a value of about 50 seemed to be a good trade-off point, um, for this particular hyperparameter. But of course, you're free to experiment with this um, on your own end for your own use case. And then the other important hyperparameter was the control weight, which basically controls how strongly each control net branch or each input modality should affect the output of the model. Basically, it determines the contribution each input modality should have to the generation process. And here you can specify a range from 0 to 1 for each of the input modalities. Um, and yeah, as I mentioned earlier, there are 4 control net branches, and you can specify a separate control weight for each of them. So you have the RGB, the depth, segmentation, and the edge modalities basically. Generally, the larger the value, the stronger the contribution of that modality, um, and the smaller the value, the greater the degree of visual augmentation or creativity you'll see compared to that modality. So, for example, if you have depth, and if you have set a very small value for the depth modality, then you might see the depth being changed in the output video. Whereas if you set a very high value for it, then you will see the depth being retained almost exactly, um, uh, as same as the input depth video. Now, a few tips and tricks with regard to this particular hyperparameter is that we found that for this use case, we found that giving high segmentation and depth weights led to better geometric preservation, because the depth and segmentation help. If firstly they help differentiate the different parts of the scene more easily, plus they specify how the various objects are placed with respect to each other, So generally, we found that setting a high weight for these modalities helped better preserve the geometry and the trajectory in general, um, and also led to more realistic outputs, while also giving a lot of freedom to the model to make visual changes, because these modalities don't offer any visual information as such. Um, their contribution is more along the geometry. So the model still had a lot of freedom to change things visually, um, assuming we set lower weights for the RGB and the edge modalities. We also found that setting a high edge or RGB weight led to worse geometric preservation and less realism. And again, that is to some extent that's because of the poor quality of the RGB video itself, or the low resolution of the RGB video itself, which makes it difficult for the model to actually get any kind of geometric cues from that video. So from our experiments, we found that setting using these particular set of weights that is mentioned here um, was the, were the optimal weights to use for this use case. And these are the same as the values that were mentioned earlier in the brackets in the previous slide. Um, I think there was a question around that, so I hope this clarifies the doubt now. Um, okay, so let's, sorry. Yeah, so here are some more examples of some more generated videos with various different prompts. Here I've not specified the entire prompts, for the lack of space, but yeah, here I've just mentioned the broad setting that was given for each of these prompts. So here you see, it's in a volcanic research outpost. Here you have an underwater lab, a biotech greenhouse, a museum, a foggy industrial scrapyard, and a jungle outpost. And again, here you see that you're able to achieve a high degree of diversity in the data, a high degree of realism in the data, with various visual effects. Um, so that really helps a lot with the uh, making sure data uh, the data is diverse and realistic for using for training robot policies on top of this. So now we can go into some results, but before that, if there are any questions, I think we can deal with any questions right now.
I think we did have a few questions. Let me bring them up right here. Some of them also were answered in the comments themselves, so thank you. The question, what happens if I generate a scene with one action and film it with several cameras and generate the variations? Does that approach make sense?
And then okay, so you have some task, let's say for example the cube stacking task, and then the question is if you film it from several different viewpoints and then try to generate variations. Okay, so in that case, one problem that you'll run into is, of course, consistency between the different viewpoints. So let's say if you want to generate, um, let's say you have four different viewpoints, like at 90 degrees with respect to each other. Um, and you feed all four viewpoints to the model in some format. Um, now, the problem generally with the transfer one model that we've seen is that it's not great at preserving this consistency between all four viewpoints, because at the end of the day, it's still only dealing with visual data, and it doesn't have a perfect understanding of the geometry and the relative positions and changes in viewpoint. So it does not do a great job of preserving um, those. So you'll still get some changes, some augmented videos for each of those viewpoints, but those changes won't be coherent or consistent across the different viewpoints. So let's say um, you have a person in the background that just walks by in one of the augmented videos from one of the viewpoints. In the second one, that movement of the person will not be completely consistent with the movement seen in the first viewpoint. So right now, actually, transfer one doesn't really support multi-viewpoint generation as such, and even for inputs it doesn't really support multi-viewpoint as inputs. I mean, you can feed it as a multi-viewpoint input either by concatenating the videos along the time dimension or spatially, where you have like four grid, like a grid with four boxes. But our experiments have shown that transfer one is really not doesn't support that function as of now, and it really isn't built for that function. Um, there's
Makes
work
sense.
ongoing for adding that kind of support in different modules, but not for transfer one. Transfer one is very specific to deal with different modalities, but with a single viewport.
Right. Makes sense. Thank you. I think we can move on to the slides themselves and
Okay,
wrap up soon as well. I think we're running a little on overboard on the time side, but we can quickly look at
sure.
eval.
Okay, sure. So here I'll just go through some uh, yeah, some results that we got from training a robot policy on this data that we have. And so first, just want to specify that the data we generated uh, contained 1,000 samples from group mimic, and then each of those 1,000 samples was augmented with Cosmos. So we got 1,000 new samples from Cosmos, and then we combined the two. So we took the original root recordings as well, uh, and the additional 1,000 augmented samples from Cosmos to get a total dataset size of 2,000 samples, and then use that to train a behavioral cloning RNN-based policy from RoboMimic. And here we see the results of that policy being run in simulation with various different settings. So here in the vanilla setting, basically the model is run um, without any visual changes to any of the aspects in simulation. And here also you see that the model doesn't really do very well. Um, Here we have, in the second video, we have changed the light intensity in the simulation. Um, um, oh, one thing I forgot to mention, so sorry. But so here the videos that we're seeing are for the vanilla model that was only trained on 1000 mimic trajectories and was not trained on any Cosmos augmented data. So this here, I'm showing this for a comparison. So here you see the model struggles with changes in light intensity, changes in light color, light texture, or changes in background basically, and changes in table texture. Whereas if you see the Cosmos trained model, basically the model that saw um, Cosmos augmented data, it's able to deal with these visual changes or visual aspects a lot better and is able to complete the task successfully in all of these cases. And here we have some quantitative, numbers or comparisons um, to see how much of an improvement we actually get with the Cosmos trained model. So here you clearly see that, for the vanilla setting, where there are no visual changes, you see that the baseline on the non-Cosmos trained model does the best, but the Cosmos model is not far behind. But for all the other settings, the Cosmos model far outperforms the baselines. Um, as you can see, like here, when we change the light intensity, the baseline 2K model only succeeds 20% of the time, whereas the Cosmos model succeeds in the task 62.2% of the time. And then same for the light color, the lighting environment, the table texture, and even the robot arm texture. Um, so yeah, we definitely see significant improvements in the trained policy's ability to deal with visual diversity and visual changes generally, um, just by being trained on that kind of diverse data from Cosmos. So we we definitely advocate using this workflow um, for scaling up data at a low cost, uh, but getting a better policy with that kind of trained on that kind of data. So yeah, that's all I had for the presentation. Here is just some additional resources that you can go through if you're interested to further check this out. One thing I forgot to mention earlier is that the data that we use for training the models that I showed earlier, we have released that data on Hugging Face, so that in case users do not want to go through the process of running Mimic or um, Cosmos at their end, they can just take the data and train a policy as needed. So yeah, you can find that on Hugging Face as well. Yeah.
Thank you so much, Shaurya. I think this was super interesting for all of us to learn more about like just not imitation learning, but about like how you can add Cosmos into this overall workflow and really help augment the data which you've already generated through group mimic. So this was super cool, and I think the results speak for themselves too. Like just adding Cosmos into the overall mix of things is really helping like models get better, and I think that really drives the point home for like maybe improving sim to real as well for your use cases. So pretty interesting. Thank you so much. I can see Admar is back. Hey, Admar.
I'm back. What a great hour! I loved watching and learning about augmented imitation learning. This is really fantastic. Such great questions and comments coming in throughout the stream. Thank you both for putting this together and also answering so many questions live. I always think this is one of the amazing things about the community is how we're all exchanging information together in real time. And I'm so grateful that our developers from our team can also make themselves available to everyone watching at these moments. Speaking of interacting with our developers, last also pitch for GTC Washington DC coming up end of October. Leverage that coupon code right there to get 20% off your conference price. Let us know if you're going so we can help you with some of your activities there. If you have a question on any of the workshops or the sessions, we're here to help. Obviously, this will be most easy for people on the East Coast to get to, but it's open to the world. So take a nice airport right there in Washington, D.C., so you can come in from anywhere. Really excited to meet new developers and existing relationships we have at GTC DC around the corner. As I said earlier, I'll be there. And then once again, really happy and excited that this hackathon is now open for registrations. We mentioned a little earlier, but for everyone watching who missed the beginning, to basically select a sim-ready object from the Revel library of real-world assets. Some great companies have donated some assets for this, including Bosch and DHL and IKEA, I believe, which is amazing. Choose your robot and demonstrate a useful application. So pretty wide open, really exciting. And we'll post the link again in the chat, but registration's open now. There's a really nice video here if you want to go to check out that webpage and that video. I hope anyone out there who's interested goes there and jumps in. Feel free to form a team. I can't wait to show off some of these robotics projects in the coming weeks. And then we're going to have a live stream recapping things with the winners. So really exciting times. Thank you both for coming on once again. Any last minute words you want to leave people with?
No, I was just thankful for the opportunity to be here and to present this work, and I hope people find it useful. And yeah, thanks for having me.
Yep. Thank you so much, Shaurya. I think like we've got so many comments praising like the depth of the presentation and the information which you walked us through. So thank you. I think it was great. Like we got to learn a lot more about imitation learning and Cosmos as well in terms of how it can really add value. So appreciate you joining us today.
Absolutely. It's been a fantastic time. Thank you both. And I just put in the chat our learning path for robotics, which is great self-paced courses that you can go ahead and dive into if this topic and more similar to that or interest you. Let us know. Feel free to jump on the Discord server. Let us know if you help with anything. We'll be glad to help. Until next time, thank you everybody for watching. Everyone out there has been really great. And Rishab and Charya, thank you.
Thank you so much, Edma. Thanks, guys.